Hello everyone. In the previous video, we studied the characteristics of JFET N-channel JFET. In this video, we are going to study about the P-channel JFET. In the P-channel JFET, the construction is the same. That is, we have the P-channel. On that, we have the N-channel, which is going to form as two N-channels or form which is going to act as source and the drain. The source and the gate terminal is internally connected, which is as shown here. The upper side of the channel is going to be the drain terminal, and the below the channel is the source terminal. For the P channel JFET, this is going to behave same as the N-channel JFET, except the voltage polarities and the current directions are going to be reversed. So when it is done with the N-channel JFET, we maintained during the operation of the N-channel JFET, we saw that the VDS, that is the drain to source voltage, was negative. That is, we used to reverse bias. Yes, we used to reverse bias the drain and gate source voltage. That is VG. Gate source voltage. But here we are going to apply the here also we are going to maintain the reverse bias only. But coming to VGS, when we apply the VGS voltage, it is going to appear with two. We operate the P channel JFETs as in the N channel JFET. We are going to operate it under the two conditions. That is, when for the N channel FET, we maintain the VGS as equal to 0 and VDS as greater than 0. And the second condition was VGS is lesser than 0, where my VGS was going negative. But here we can VGS, since it is a P channel JFET, my VDS, that is the condition is not negative, my VGS is greater than 0, that is it is a positive voltage, right? So the high levels of VDS, that is it says that the high levels of VDS, the JFET reaches a breakdown situation. ID increases uncontrollably if VDS is greater than VDS max. When we look into the transfer characteristic curve, where we plot against VDS versus ID by keeping VGS as constant, it shows that my VGS is a positive voltage, and as and when I vary the VDS, my IDS is going to increase. So as VGS increases more positively, the depletion region zone is also going to get increased and ID decreases. That is, the current is going to get decreased. As and when we observe the characteristic curve here, we can see that as and when the VGS voltage is going to get increased, the ID is getting decreased. Eventually at some point our ID is also going to become 0 ampere. Now, let us have a gist of what we studied about the JFETs. We came to know our JFET has two types. One is the N-channel JFET and the other one is a P-channel JFET. For the N-channel JFET, the representation is the arrow mark inside, and for the P-channel JFET, the arrow mark that should be indicated on the gate terminal should be outside. So this is one thing we studied. and we also studied some of the important parameters that we have to remember. For the N-channel JFET, always remember my VGS as equal to 0. My ID would be equal to IDSS, right? Where this is going to happen, this is nothing but my ohmic region condition. So this is nothing but our ohmic region condition. Similarly, when we go for the cutoff region, there VGS is less than pinch off level. That is, we say that whenever in the cutoff region the gate source voltage is negative, right? So that is nothing but my VGS is equal to minus of VP, correct? So pinch off voltage, that is what, when ID is equal to 0 ampere, this is going to happen. And the very next parameter that we should remember here is the pinch of voltage, that is VP. Whenever my pinch of voltage is very much greater than VGG, which is very much greater than or equal to 0 volt, my the ID is going to vary between 0 ampere and IDSS for VGS lesser than equal to 0 and greater than the pinch off level. So let us have a brief look, brief discussion on the JFET transfer characteristics, wherein which we are going to study the Schottky effect, Schottky equations. So it is given by ID is equal to IDSS into 1 minus VGS by VP. So what is your VGS? IDSS, this is the maximum current that where the current is going to get increased and the device is going to behave as a behave in the ohmic region. And similarly, what is your VGS? VGS is going to vary whenever whatever the condition, and VP is nothing but we also say VP as a VGS off condition. So it is nothing but VP is, if it is an N-channel JFET, then this becomes a negative voltage. If it is a P-channel JFET, and this becomes a positive, right? So in a JFET, the relationship of VGS input and ID output is defined by the Schottky equation, and it is given by this. Let us have a look at the transfer characteristic. We can study the characteristic of N-channel FET and J-channel FET, P-channel JFET in two forms. One is the transfer characteristic and the other one is the drain characteristic. For the transfer characteristic, we always plot a graph of ID versus VDS, keeping my VGS as constant, and for the drain characteristic, we plot a graph of ID versus VGS by keeping our VDS as constant. Getting the difference? What is the transfer characteristic states? It is nothing but the plot of ID versus VDS by keeping VGS as constant, and my drain characteristic is plotting of ID versus VGS by keeping VDS as constant. So when we look into the transfer characteristic curve, we can when we observe here in the N-channel JFET, I can say as and when my VGS is going negative, my current IDS is decreasing. So whenever it reaches the positive, that is whenever my VGS is equal to 0 volt, I can expect my IDS as maximum. That is whenever it becomes positive, my IDS is going to become maximum. Similarly, when we come for the drain characteristic, we can have the inference saying that as and when in the drain characteristic, we are going to keep our VDS as a constant voltage by varying the VGS. We already know VGS, when we have to vary the VGS, we are making it as a lesser than 0, right? It is always lesser than 0. It is almost, we are making VGS as equal to 0 where we enter into the pinch of voltage. So what is going pinch of region? So as and when you decrease your VGS, we can see our IDS is going to become 0 amperes. So it is entering into the pinch, cutoff region. Yes, my IDS is going to reach the cutoff region rather than the saturation or the pinch off region. So as and when, look here, as and when the VGS is becoming 0, we can say my IDS is equal to 0, right? So this is the transfer characteristic and the drain characteristic of N-channel JFET. Similarly, for the P-channel JFET, you have the same characteristic curve to be plotted. That is, for the transfer characteristic, same thing. We keep we plot a graph of ID versus VDS by keeping VGS as constant, where my VGS is now positive. As in when you make a negative, it is going to become 0. That is, my voltage, my current is going to decrease. Similarly, when we plot a graph of ID versus VGS by keeping my VDS as constant, I can say it is going to reach, that is always for the P channel JFET, remember it is a positive value of a VGS. Yes, so this is about the transfer and the drain characteristic. So what is the important relationship that we have to study here is we have the N channel JFET, whether it could be a N channel JFET or whether it could be a P channel JFET. Let us look into the respective currents and voltages. So the current which is coming from ID, we call it as drain current. The current which is coming from gate, we call it as gate current, and the current which is coming from the source, we call it as a source current. The voltage between the gate and the source, we call it as VGS. The voltage between the drain and the source, we call it as VDS. So the current ID is given by IDSS of 1 minus VGS by VP whole square, which is nothing but the Schottky current equation, right? Now ID is equal to IS and IG is also approximately equal to 0 ampere. So when we go for the BJT, I can say my collector current is given by beta into IB, and IC is equal to IE and VBE is equal to 0.7 volt. So these are some of the important relationships that we can have between the JFET and BJT. So hope this video is very useful to you. Thank you for watching.